Hello again, students. After taking rest, we are ready to continue our lesson. In the previous session, we talked about distributed systems and real-time systems. We also studied some simple scheduling algorithms of real-time tasks. And so, in this session, we continue our discussion. Real-time systems, in fact, there are different applications. Real-time systems generally fall into two main groups. I mean, categorized into categories. The first group is about hard real-time systems, and the second group called soft real-time systems. What's the difference between hard real-time and soft real-time systems? Hard real-time systems are those systems that missing too many deadlines results in a catastrophe or in a disaster. Can you hear me? Is everything okay? Well, as I said, hard real-time systems are those systems that missing too many deadlines usually results in a catastrophe or in a disaster. What is catastrophe? What is disaster? What is disaster? فاجعه. Yes, exactly. And what is فاجعه? What is فاجعه? Okay, tell me, what do you think about فاجعه or karate or disaster or catastrophe? You use it in your conversation every day, okay? What does it mean? There is not any homework yet. There is not any homework for you, okay? I asked you about فاجعه. What is it? There are many phrases that we use it every day, but we are not able to explain them. So it's good sometimes you deeply think about the phrases you are using. فاجعه, catastrophe doesn't mean anything, really. It doesn't mean. For example, something happens and you say, wow, it was a catastrophe, it was a disaster. So tell about it. No. Something bad. So what is something bad? I mean, I want you to explain something bad. What is it? For example, if you lose your mobile phone, it will be something bad. So it will be a disaster. So what is disaster? In general, when some people may lose their lives, and in some situations that people may be killed, it would be disaster. Okay, for example, in airplane, in train, in car. Okay, so it will be a disaster. Also, if you lose a huge amount of money, it will be a disaster too. A huge amount of money. If you lose a huge amount of money, so it will be a disaster too. Or sometimes some harmful may occur about nature. For example, in a chemical plant. Chemical plant means how to explain it? Or nuclear plant. Or a nuclear plant. If a bad accident occurs in a nuclear plant, it affects nature, so it will be a disaster too. Got it? So many real-time systems are hard real-time systems. I repeat it. Hard real-time systems are those systems that mean missing too many deadlines results in a disaster. To name some examples, airplane, train, car, and medicine. But soft real-time systems are those systems that are still real-time but missing too many deadlines will not result in a disaster. It affects only on quality. Only on quality. Like Adobe Connect and video conference we are using at the moment. We are using a real-time system. It's a kind of DMMS, distributed multimedia system. It's real-time because it's important that you hear my voice real-time. The frames and the packets have deadline, but missing too many deadlines will not result in a catastrophe. It's not disaster. It affects only quality. So it is called soft real-time systems. Got it? Good. So, do you think DMMS is a soft real-time system or hard real-time system? Distributed multimedia system is a hard real-time or soft real-time system? It depends on the way that we use it. I think hardware. Hardware, no. Hard real-time or soft real-time? Hardware and software, no. Hard real-time or soft real-time? The deadline is hard or soft? It's about deadline. Hard deadline or soft deadline? Yes, it depends on the application. It depends on the application. So the system is not soft real-time or hard real-time. The system is DMMS, Distributed Multimedia System. We cannot say it is a hard real-time or soft real-time. It depends on the application we use it. If the application is Adobe Connect for a video conference between you and me for e-learning, distance learning, so it is a soft real-time system. Why? Because missing deadlines will not result in a catastrophe or disaster. But if we use DMMS or Distributed Multimedia System in a surgery, distant surgery, so it would be hard real time. For example, as your friend said, assume that we have a surgery in Tehran and a doctor in Germany controls the operation room. So he is using DMMS2, but in this case, DMMS is a hard real-time system because missing too many deadlines may result in catastrophe. The patient may be killed. So in this case, in this application, it is hard real-time system. Clear? Good. Very good. So I gave you some fundamental and basic information about real-time systems. Currently, you completely know what are real-time systems and what are the main properties and what's the difference between real-time system and distributed system. In real-time systems, there are many areas that you may be interested to study. For example, about scheduling algorithms, about different environment, single processor and multiprocessor, and also about reliable real-time scheduling, primary backup techniques, and many other different areas. If you are interested, you can study it, but it's not our main focus. We do not focus on real-time system in this course. Our main focus is about distributed systems. Okay, it was some basic information about real-time systems to get you familiar with such systems. Okay, so a new type of systems, distributed real-time systems. You know what is distributed system. Also, you found what is real-time system. And now, combination of these two types of systems. Distributed real-time systems. In the real-time computer system, if you use a real-time communication network to connect computers and machines, then you will have distributed real-time system. As an example, DMMS is a distributed real-time system. I said to you, DMMS is distributed because it's distributed multimedia systems. And I added that this type of system is real-time because you want to watch a football match live, so it's real-time. It is called distributed real-time system. Before I explain and I talk about this slide, I want to ask you a question. How can you access to your important data when you are traveling? How can you access to your important data and information when you are traveling? When you cannot access to your laptop or PC. So how can you access to your information? There is no difference. DMMS is distributed real-time system. DMMS is distributed real-time system, in fact. It is an example of distributed real-time systems. Yes, In fact, with the increasing maturity of distributed systems infrastructure, a number of companies, a number of corporations are promoting the view of distributed resources as a commodity or utility. I mean, distributed resources such as storage space, such as processors, as a commodity or utility. Commodity or utility means, I don't know what does it mean in Arabic, but vasile, it means vasile. Some corporations uses distributed systems as a utility to make money. Okay. For example, Google provides you free storage space, so you can use it to upload your important information, pictures, I don't know, movies, etc. Okay, and you can access to your information everywhere, all over the earth, all over the world, in Iran, in Iraq, in the US, or anywhere. You can access to your information. So, if you want more space, you must pay money to Google. Also, Microsoft OneDrive provides you the same service. It's a distributed system because when you are working with your OneDrive or Google Drive account, you think that you are working with a single system. You don't see the system as a distributed system. But in fact, the system is distributed. You don't know where is the server is located, and how your file is stored on the servers, how the backup is being done. You don't know anything about it. So it is a distributed system, but it is a utility to make money. It is called cloud computing. Have you worked with Google Drive? If not, at the moment you can type drive.google.com. So if you sign in to your account, you can see your free storage space there. Clear? Got it? It could be a kind of big data. It could be. But it is really for making money. With this model, resources are provided by appropriate service suppliers such as Google, Microsoft, Amazon. And what I mean by resources are exactly about, you can see here. Let me change the zoom size. Application services, storage services, and computational services. You can use these services. Storage services such as Google Drive. Google Drive is also an application. You can use Google Drive to open your Access and Excel file, your Word file, your PDF file, even though you don't install the Microsoft Office on your laptop. But if you use Google Drive, you can use this application to open your Excel files and PDF files. So it is application. Also, it provides you storage space. So it's about storage too. How about computational services? How about computational services? Okay, I explained and I talked about application services and storage services that corporations can provide for you. But how about computational services? How you can use computational services? Okay, it's the internet, but how? Give me an example about computational services. Not exactly. Google Drive. Listen to this example. Suppose you have a problem with a heavy computational complexity. It means you need an extensive computational resources, for example, CPUs, to solve your problem. It needs a long time to be solved. So if you use your laptop or your PC to solve this heavy problem, it takes, for example, 1 week or 2 weeks to solve this problem. But if you use some computational resources such as processors that cloud computing provides you, you can solve your problem in a few hours, because the corporation gives you a very powerful processors to solve your problem. It means you upload your problem to their servers and execute your program on the server of the corporation, for example, Amazon. Okay, you use their processors to solve your problem. It is computational resources, in fact. Well, so cloud computing could be another good and interesting area of research in distributed systems too. If you search on Google Scholar, you can find many papers and articles about cloud computing. It's very interesting. It's very wide. It has very important fundamental issues and aspects, and so I think it has many aspects to study. So it would be a interesting area for research too. It's a kind of distributed system. So you can see distributed systems are very, very vast, are very I don't know. Nowadays, in our world, I can say that distributed systems saves the first word and the last word. Cloud computing, supercomputing, and also DMMS, distributed multimedia systems, they are all distributed systems. So another area is parallel computing. I want to compare parallel computing with distributed system, and we want to see if they are the same or they are distinct. What is parallel computing? As you can see, parallel computing is a type of computation in which many calculations or processes are carried out simultaneously at the same time. Large problems can often, not always, but can often be divided into similar ones, which can then be solved at the same time. I think the definition is clear, but if I give you more detail, I can say that there are some problems in our world that we can divide them into sub-problems, smaller sub-problems, and then execute each sub-problem on a different machine. All the machines at the same time starts to execute their sub-problems. So we can solve the problem faster than when you use single computer to solve the problem. Was it clear about parallel computing? Parallel means موازی، محاسبه موازی. In this picture, you can see we have a main big problem here. It's our main big problem. You can see we divide this problem into smaller problems. You can see here 4 smaller problems or 4 sub-problems, and then every processor or every machine can solve one sub-problem. The machines starts the execution simultaneously at the same time, so we can solve the problem faster. This is parallel computing. Okay, so let me give you another example. Assume that we are given an array A with a length of 100. We have an array with a length of 100 elements. The problem is to calculate and to add all the elements of the array, A0, A1 until A99. We want to add all these elements. In the first situation, we have only one student, okay, and I ask this student to calculate and add these elements. So the students must add A0 plus A1 plus A2 and so on. In the second situation here, assume that we have 10 students, not one student. We have 10 students. So I break the problem into 10 sub-problems. So the first student is responsible to add the first 10 elements, A0 until A9. It is the duty of the first student. The second student is wanted to add the second 10 elements. The second 10 elements of the array means A10, A11 until A19. The third student here, I didn't write, but you know, the third student is responsible to calculate the sum of the third 10 numbers of the array, and so on. Lastly, here, the last student, student 10, the last student is responsible to add the 10 elements of the last of the array. I mean the final elements, A19, A91 until A99. And all the students starts to calculate simultaneously at the same time. So you can guess that in this situation we can solve the problem faster, very faster in fact. It is parallel computing. Got it? Was it clear? Okay, I repeat it again. I said in the first situation here, we have only one student, and I ask him to calculate all the numbers, to add all the numbers, all the elements. Okay, so he must add 100 numbers. In the second situation here, we have 10 students. So I break the problem into 10 sub-problems, and every student is responsible to solve its sub-problem. The first student is responsible to calculate sum of the first 10 numbers, A0, A1 until A9, the first 10 elements. The second student here, he is responsible to calculate sum of the second 10 elements. I mean A10, A11 until A19, and so on. In this situation, we have 10 students, and all students starts their work simultaneously at the same time. So we can solve the problem faster. It is called parallel computing. Yeah, the first situation is about serial execution of the problem, and the second one is about parallel execution. You're welcome. You're welcome. But please keep in mind that in parallel computing, we have to pay cost. it is costly for us. What is the cost in the parallel computing? What is the cost? What is the cost in parallel computing? I'm talking about cost. Yeah, cost. هزینه. What is the cost in parallel computing? We have more computing resources, or we need more computing resources. We can solve the problem faster, but the cost is about computing resources. Okay, but in serial computation, here the first case, we only have one student, so the cost is not about computing resources. Here the cost is about in the first situation, when we use one student, the cost is not about computing resources. It is about time. Exactly. In the first situation, the cost is time. It is time consuming. It is time consuming. If we want to solve the problem faster, so we must pay the cost. And the cost here is about computing resources. Yeah. Okay. This problem is a problem that we can break it into smaller problems. You saw how we broke it. Okay. But there are many problems that we cannot break them into smaller problems. In such situations, we cannot use parallel systems. Parallel computing is only useful for those problems that we can break them into smaller problems. Okay. Now tell me about I have a very important question now. In the second situation, when we use 10 students, do you think, is it necessary to communicate between students? Is it necessary to connect students with a link or communication network? Yes, the issue is about, for example, let me think about it. we must connect the students, because when every student calculates its problem, its sub-problem, for example, the first student, the second student, so what do we have? What do we have? We have 10 students. Each student have a number. So we must add these 10 numbers. So the first student must send its result to the second student, and the second student will add these two numbers. The third student must send its result to the fourth student, and the fourth student will add these two numbers. And the fifth student will send its result to the sixth students, and student number 6 will add these two numbers again, and so on. Again, we have the same pattern for the second student and the fourth student and the sixth student and the eighth student and the student 10. So we need to connect them with a network. There must be a communication link between students. We have different steps in solving this problem. I must say that we break the problem into sub-problems and then solve every sub-problem by a student, and then in the next step we must gather the results and combine them to make the final result. Have you heard about knapsack problem? Have you heard about knapsack problem? For example, 01 knapsack problem. No? Really? Wow. But I think you have heard it about it in bachelor in data structures course, or maybe in algorithm design. I don't know, but knapsack problem is a very famous problem in computer science. You cannot use parallel computing to solve it. You can search about it and read the problem, and so this is a problem that it is not possible to break it into sub-problems. What is it, students? This picture, in fact, shows a very powerful computer. Or to be honest, it shows a supercomputer. I'm sure that you have heard supercomputer. It is Blue Gen. It is made by IBM Corporation. Supercomputer use parallel computing to solve problems. So you can guess that these supercomputers contain many processing elements, many processors. So each processor can be used to solve a sub-problem. In this case, as you can see, there are many cabinets. And every cabinet contains many processors. Like the previous example, we used 10 students to solve the problem. Here in supercomputer, we use thousands of processors to solve heavy and big problems. These processors are connected to each other by a network, by a very fast network, in fact. And supercomputing is a good idea to make a computer more powerful. Traditionally, computer software has been written for serial computation. To solve a problem, an algorithm is constructed and implemented as a serial stream of instructions, one after the other instruction. Okay. So to make computers more powerful, we had to increase the frequency of the processor, frequency of the processor. For example, if we had a processor with 2 gigahertz frequency, to make it 5 or 10 times faster, to make it 10 times more powerful, faster, we had to produce a processor with 10 gigahertz frequency. It was impossible. If we could do, it was so expensive, very expensive. Instead, if we use 5 processors, each of which has 2 gigahertz frequency, and connect them, so we can make a computer with 10 times more powerful. But this situation was very, very cheap in comparison with the first solution. Got it? It was clear? Instead of making a processor with 10 gigahertz, that it is very expensive, we can buy 5 processors, each processor 2 gigahertz, and connect them together. So we have the same power with less money. Okay. Supercomputer uses this strategy. Supercomputers use this mechanism. It is a very powerful computer containing thousands of processors. Each processor is a very normal processor, like the processor we use in our laptop, 2 gigahertz, for example, frequency. So the processors are not so advanced. but connecting these processors together make a supercomputer for us, and it's very powerful in fact. Here, the hierarchy of BlueGen processing units. In the previous picture, you saw some big cabinets. Okay. Here, you can see big cabinets. In this picture, you see that the system contains 64 cabinets. I mean, here there are 64 cabinets for BlueGen, a supercomputer of IBM. 64 cabinets. Each cabinet has 2048 CPUs. You can see each cabinet has totally 2048 CPUs. So there are many CPUs in this supercomputer. How many CPUs uses the BlueGen? How many CPUs uses BlueGen? 64 cabinet. Each cabinet has 2048 CPUs. So there are more than 100,000 CPUs. It's very big, very huge. Yes, exactly. It's very huge. It's the number of processors that the BlueGen uses. How the BlueGen and supercomputers solve the problems? Exactly like this example. Exactly like this example. The problem must be broken into smaller problems, and every CPU is responsible to solve the sub-problem. What is the most powerful supercomputer in the world? What is the most powerful supercomputer in the world now? Search it. Google it. Search on Google. The most powerful supercomputer. Do you like to search the word to find the most powerful supercomputer? It is possible for now. At the moment, we can search to know what are the most powerful supercomputers and where they are. Just open your internet browser and Google top 500 supercomputers. Yes, if you Google top 500 supercomputers list, the Google will show you a very useful website that can tell about supercomputers. Google top 500 supercomputers list. The top500.org website tells you about 500 top supercomputers of the world. And as your friend said, here, Fugaku from Fujitsu in Japan is the most powerful supercomputer in the world. It's parallel computing. It is parallel computing. How many processors does Fugaku use? How many processors does Fugaku use? How many processors does Fugaku contain? How many processors does it use? Tell me the answer. You can find the answer in top 500. Okay, it's Fugaku. How many processors, how many CPUs does it have? Yes, in top500.org website, you can see some useful information. The number of CPUs, as Mustafa Saleh said, is more than 7 million processors. 7 million processors. It's very amazing. 7 million processors you can find in Fugaku. Just imagine. Yeah, it's really big. It's really huge. Really, really. So, look at the picture. In Fugaku, can you see some links that connected cabines together? Cabinets are connected to each other. So we are connected processors together. There are more than 7 million processors. Each processor can be assumed as a machine. It's a computing machine. They are independent. They are connected to each other through a network. So can we see this system as a distributed system? What do you think? Can we see parallel computing as a distributed system? Think about it. We talked about it next session. We will talk about it next session, okay? So I think it's enough for today, and we had a good and useful conversation. I think we learned many things today about different aspects of distributed systems and parallel systems, distributed multimedia systems, also real-time systems, and now we have a huge knowledge about different types of prominent systems now. So, okay, if you don't have any problem and question, we can finish this session. خدا حافظ. إلى اللقاء. Have a good night. Bye.